Previously, we talked about torsional force. When a reinforced concrete member is subjected to torsional force, the member tends to twist. This twisting response leads to tensile stress developed within the member. As you know, concrete is poor in tension. When the tensile stress exceeds the concrete tensile strength, diagonal crack happens. Now, in order to control the development of the crack, you need the longitudinal bar as well as the shear link as the reinforcement. This reinforcement acts as the tension member in reinforced concrete, assuming the concrete carry no tensile force. All the tensile stress shall be taken by this reinforcement. Because of this arrangement, it leads to an analogical truss structure, where the steel reinforcement acts as the tension member, whereas the concrete acts as the compression member. Due to the truss action, there will be compressive strut within the model. And then what are the mechanisms of failure? You have this reinforcement taking the tensile force, and you have concrete taking the compressive stress. Either one of them fail, that means the member will fail in torsion. Now let us talk about the working mechanism of a reinforced concrete member subjected to torsion. We assume that the member here is a thin wall box section, even though it is a solid member. The box here is reinforced by the steel bar at each corner with shear link as a loop, being the transverse tensile tiles, and the concrete as the compressive diagonal strut. The torsional force here will lead to shear flow acting within the thin wall box. We use simple Q to represent the shear flow. And this shear flow acts in the perimeters of this thin wall box. Now, how do we calculate the shear flow? It is calculated by multiplying the shear stress with the thickness of the box section. This represents the thickness. There are mechanisms for us to determine the effective thickness, which we're going to discuss in detail in future. At the moment, you just need to remember there will be shear flow acting onto a member subjected to torsional force. And this shear flow is calculated based on the shear stress multiplied the effective thickness of the box section. Now, from the classical elastic theory, the applied torque can be related to the shear flow as expressed by this equation. It is the functions of the shear flow multiplied with the area of the box section. This represents the area of the box section. The formulas for the area of the box section is given here. The basic principle is this. Let's say you are dealing with a solid section. Its torsional resistance would be similar to a box section, where the middle part of the section here offer very little contributions to the torsional resistance. That's why we call this as an equivalent box section. As the torsional resistance is calculated on the basis of the effective area of the box section, that means the gross area cannot be used, even though it is a solid section. You are supposed to use the effective area, representing this area. Now, how do you get this area? First, you need the effective thickness. Taking the width minus half of the effective thickness and half of the effective thickness. That gives you B minus the effective thickness. You will do the same for the height. Take the H minus half on top and half at the bottom. That gives you the H minus TEF. By multiplying this width and this width, you get the effective area. Now the problem here is how do you get this effective thickness? This is calculated on the basis of this formula, which is a ratio of this gross area divided by its perimeter. The gross area is calculated by B multiplied the H, whereas the perimeter you have B plus B plus H plus H, all four sides of the member. With that, you get the effective thickness, and this effective thickness to be substitute into the formula here to get the effective area. From the effective area that you have obtained, multiply with the shear flow, that will be your applied torque, which is the torsional force. Now you might want to ask, what if the section is actually hollow? Would the calculation be the same? Not quite. Basically, the formula for the effective area and the effective thickness are the same, except that there is an additional considerations related to the actual thickness of the hollow section. On top of the basic calculations to determine the effective thickness, which is the ratio of the gross area divided by the perimeter, you need to compare the calculated effective area against the actual thickness and also the concrete cover. The area here represents the gross area. You don't have to minus the internal part here. Whereas the perimeter here represent the outer perimeter, not the inner perimeter. From the formula here, you get the effective thickness. Check with the actual thickness. Your effective thickness cannot be greater than the actual thickness. If your actual thickness is greater than the effective thickness, you will use the effective thickness, assuming the internal part here contribute nothing to the torsional resistance. Also, your effective thickness must be greater than 2 times the concrete cover. If it is less than 2 times the concrete cover, the hollow sections is considered inappropriate, unable to generate sufficient resistance to the torsional resistance. You might want to ask, why is it so? Why must it be greater than 2 times the concrete cover? To be frank, I have no idea. I believe it has something to deal with the bonding with the reinforcement, since our design is on the basis of the analogical truss model between the reinforcement and concrete. You need sufficient cover from the concrete so that adequate bond between the reinforcement and the concrete can be generated. Correct me if I'm wrong. Now let us simulate the possibility here. Let's say you have calculated the effective thickness and you realize that the effective thickness is less than 2 times the concrete cover. That means the hollow sections is inadequate. You will need to redesign the section. Let's say now the effective thickness is greater than 2 times the concrete cover. You're going to check your effective thickness against the actual thickness. If the effective thickness is less than the actual thickness, that means there will be parts of the hollow sections are not contributing to the torsional resistance. Therefore, the non-contributing part shall be trimmed, leading to an equivalent box section for you to calculate the effective area so that you can get the torsional resistance. How about when the actual thickness is less than the effective thickness and the thickness is actually more than 2 times the concrete cover? Shall you use the effective thickness or shall you use the actual thickness? This condition is not mentioned in the reference that I have referred. Maybe I overlooked that. However, by solely look at the formulas here, it is likely that you need to redesign the hollow section. Make sure your actual thickness shall be at least the effective thickness, not less than the effective thickness. You cannot simply take the actual thickness. In the case that your actual thickness is actually thinner than the effective thickness, if you use the actual thickness, that will give you a higher effective area. This might lead to a situations where you might overestimate the applied torque. And in the case that your actual thickness is actually thinner than the effective thickness, you cannot simply use the effective thickness either, as that does not really exist in the actual condition. Therefore, based on my current understanding, if either of this is not fulfilled, that means your effective thickness is greater than the actual thickness, or the effective thickness is less than 2 times the concrete cover, you need to redesign the hollow section.